Used cooking oil is commonly produced from domestic and industrial food preparation. Repeated heating and reuse cause physical and chemical degradation of the oil and led to the accumulation of inorganic contaminants, particularly sodium and potassium, natrium and kalium respectively. In Malay, that is, which originates from cooking salt, food, ingredients, and frying process. High concentration of these metals are undesirable, especially when used cooking oil is reused, recycled, or converted into biodiesel, as they can interfere with processing efficiency and deactivate catalysts. Therefore, accurate determination of natrium and kalium is essential for quality control and environmental assessment. In this study, sodium and potassium is used in used cooking oil were analyzed using flame photometry following acid digestion to convert the oil matrix into aqueous solution suitable for analysis. First step, we filter down our used cooking oil using a filter paper. We weigh down 2 grams of used cooking oil for our experiment, as you can see there. Then Then we add 10 milliliter of concentrated nitric acid to the beaker that is filled with 2 grams of used cooking oil. Then we put the beaker filled with 2 grams of used cooking oil and also 10 milliliter of concentrated nitric acid on top of a hot plate. We let the nitric acid and plus used cooking oil solution to cool down to room temperature, and then we add 10 milliliters that of deionized water to the mix. We then transfer the mixture of 10 milliliter of concentrated nitric acid and also the filtered used cooking oil to the volumetric flask, and then we fill the volumetric flask to meet the what's that again? The line on the volumetric flask using the ionized water. First, we transfer a known volume of Na stock solution to a volumetric flask using a clean pipette that the volumetric flask already filled with the ionized water beforehand. Then we filled the volumetric flask that already filled with the Na stock solution and the ionized water. And again, we filled it with the ionized water until the mark is reached on the volumetric flask. We transferred 2 milliliters of Na stock solution with known volume to the 100 milliliter of volumetric flask, and then we filled it with the ionized water until it reached the mark on the volumetric flask. We put 2 milliliters of NA's known volume of Na stock solution to the 100 milliliter volume. We put 2 milliliters of known volume and a stock solution to the 100 milliliters volumetric flask that is already filled with a bit of the ionized water. Then we fill the volumetric flask with the ionized water until the ionized water reach the mark on the volumetric flask. After that, we close the volumetric flask and then shaken well to get homogeneity. Then we transfer the stock solution to a more suitable container so that it is easier to be analyzed by the instrument. In this case, it's a beaker. First, we rinse the instrument inside using a distilled water, I guess. Using a water first so that there is no contaminant inside the instrument when we analyze the sample. Then we tune the instrument so that it will be more suitable to analyze the concentration of Na in the sample. It is also can be done. It is also can be tuned for concentration of K as well, kalium. Then we test for the concentration of natrium and potassium using the instrument, and the test is repeated 3 times each. And then the finding is recorded and tabulated on the data and also in the graph, in the table and the graph. For what is that again? For each concentration, for to make a calibration graph for potassium and also natrium.
The graph illustrates the relationship between concentration and emission intensity for sodium and potassium measured using flame photometer. As the concentration increases, the emission intensity for both elements decreases, showing a nonlinear and inverse relationship rather than a direct proportionality. At lower concentration, around 2 mg per liter, both sodium and potassium exhibit a high emission intensity, with potassium showing a slightly higher intensity than sodium.
However, as the concentration increases to about 4 mg per liter, the emission intensity drops sharply, particularly for potassium, which may be due to the self-absorption, ionization effects, or flame saturation. At higher concentrations, about 6 to 8 mg per liter, the emission intensities for both elements become very low and nearly constant, indicating reduced sensitivity and poor analytical reliability. The combined graph allows direct comparison of the photometric response of sodium and potassium under identical experimental conditions. Overall, the graph suggests that accurate quantitative analysis for NA and K should be performed at lower concentrations, where the instrument response is more sensitive and reliable.
Next, moving on to the discussion part. In order to calculate the concentration of sodium and potassium, we need to read the concentration of those sodium and potassium based on the calibration curves that had been recorded in the result part. So for sodium, we have obtained the concentration of 5.2 milligrams per liter, and for potassium, we have obtained 2.4 milligrams per liter, and then we inserted the concentration value into the formula of C times V over mass of oil sample. We have obtained the final concentration of sodium is 260 milligrams per kilogram, and the potassium is 120 milligrams per kilogram.
Assalamualaikum warahmatullahi wabarakatuh. Today I will discuss on discussion 3 of question 3, the comparison with literature on this experiment, or the regulatory limits or the act. In this case, we use Na, which is sodium, and K for potassium in cooking oil, so there are no maximum limits that exist either in Malaysian Food Regulation 1985 or Codex Alimentarius. So we use Codex Alimentarius and Malaysian Food Regulation 1985 as a comparison. Okay, other comparison with literature is that based on our results, we got 260 milligram per kg for sodium and 120 milligram per kg for potassium. The typical refined oil are usually below 50 milligram per kg for sodium and 20 milligram per kg per potassium. So the observation here is our samples show higher mineral content than standard highly processed oils. That's all for discussion 3. Thank you.
In question 4, why is acid digestion necessary before flame photometric analysis of oil samples? So first is to break down the oil matrix. So the cooking oil is a complex organic mixture, so it cannot be directly aspirate into the flame photometer. So that's why the acid digestion chemically decompose the organic metals into a clear solution, so it can be easily to detect by using flame photometer. Next is convert metals into the measurable ionic form. So the sodium and potassium in oil may be trapped in the oil phase. So the acid digestion release this metal and convert them into the ionic form, such as Na plus and K plus. So that can be easily to detect by using flame photometer. And the last one is ensure all aniline is extracted. So the direct dilution of oils often fails to extract the metals completely. So the acid digestion ensures that all sodium and all potassium in the sample are available to detect by using the flame photometer. So in question 5, explain the principle of flame emission for sodium and potassium. So first, atomization in the flame. So when the solution containing sodium, like in ionic form, Na plus or K plus, is sprayed into the flame, so the solvent evaporates and the metal ion are converted into the free natural atoms. Next, excitation by flame energy. So the heat of the flame excites this atom and causing their outer electron to move to the higher energy level. Next, emission of characteristic of light. So as the excited electron return to their ground state, they release the energy in the form of the light at the characteristic wavelength. So sodium emits strong yellow at about 589 nanometer and the potassium emits violet light at the 766 nanometer. And the last one, measurement by flame photometer. So a flame photometer isolates this wavelength using optical filter and measure the light intensity to determine the amount of sodium and or potassium are present. That's all.
For question 6, state two possible sources of errors in this experiment. First, incomplete acid digestion of the oil sample. If the nitric acid digestion is insufficient, Na plus and K plus may not be fully released into the aqueous phase, leading to underestimation of their concentrations. Second, instrumental or aspiration instability. Variations in flame temperature, inconsistent aspiration rate, or blockage of the nebulizer can cause fluctuating emission intensity readings, affecting accuracy and precision. For the last question, suggest an alternative analytical technique for Na and K determination. So the other alternative analytical technique is atomic absorption spectroscopy, which is known as AAS, which is a suitable technique as it provides higher sensitivity and selectivity for metal ions such as sodium and potassium, especially in complex matrices after acid digestion.
In conclusion, the flame photometry are successfully used in order to determine the concentration of Na and K, that is natrium and kalium respectively. The sample preparation, such as filtration and also acid breakdown, are essential in order to turn the oil matrix into the solution suitable for analyzing in the flame photometry. The calibration curve prepared from Na and K standard solution are proving that there is correlation between the emission spectroscopy and also the concentration of the natrium and kalium, and thus flame photometry prove that it can be useful and also essential in order for analysis of used cooking oil for environmental and also for recycling purposes of the cooking oil.